Quiz 1. A current of 2 amps flows through the resistor R1 as shown below. If they hadn't put the 2 amps there, Chantel, I would write the 2 amps in. If they find something, if you know something, if you figure something out, add it to your diagram, because suddenly, knock, knock, you might have 2 things. I guess that's going to be downhill, that's going to be downhill, that's going to be downhill, that's going to be downhill. What's the current flowing through the 5 ohm resistor? Well, the current's going to split up. I could try, I can't combine these because I don't know R2. I can't go 1 over R parallel plus 1 over R parallel. Wait a minute, though. These are parallel resistors. So how many volts along this path, Ibrahim? How many volts must be along this path? Knock, knock. I know 2 things. And all they want is the 5 ohm resistor. Okay, the current in the 5 ohm resistor is going to be V over R. 8 divided by 5, which is 1.4? No, 1.6? D? Yes? Didn't need to rewrite it. Other thing I could have done, given you this very same diagram and said, find R2. Because now that I know the amps, how many amps down here? 0.4, right? 2 amps splits up. 1.6 goes that way. 0.4 goes that way. And now I can tell you R down there. Or I could have given you the same diagram and said, how many watts in resistor R2? Well, now that you know voltage and current, V times I. So I can reuse these diagrams and just ask different questions. Often you'll see I've just changed the numbers because it's a pain to draw circuit diagrams in Word. Number 2, 3 identical light bulbs are placed, identical, same R. Which of the following is correct? The voltage and current are the same for all 3 bulbs. No. Blah, blah, blah. You know what? I could do this algebraically. I think I'm going to put some numbers on here. I'm going to let this be a lovely 60 volts. I'm going to let this be 10 ohms, 10 ohms, 10 ohms. Oh, how many volts? How many amps? Oh, how many volts must these add up together? That path must also be 60 volts. How many ohms is this whole path? So this whole path, 60 volts. This whole path, 20 ohms. How many amps? This whole path, 60 volts. This whole path, 20 ohms. How many amps? Gotta be. Okay, so how many amps right here? 3. How many amps right here? 3. How many amps right here? 3. How many volts right here? 30 volts. How many volts right here? 30 volts. And now I can answer the question for my made-up numbers. No. The current in Z is less. No. The current is greater. I think so. The voltage is less than. No. Gotta be C. You could have done that just with Kirchhoff's laws, intuitively, algebraically, but my point is don't be scared to make up nice numbers because probably it'll fall apart for you. Number 3, total current leaving the battery. I'm definitely starting right there. I see 2 things. Actually, first, I'm going to label downhill. Okay, I can tell you the current right there. The current is going to be 8.5 divided by 60. 8.5 divided by 60, and I get 0.1417. I'm going to go 0.14167 amps. 0.14167 amps. Is that correct? Okay. What else do I know? Well, That's not total current. Let's try skiing. Oh. Chantel, how many volts going along that branch? How many volts going along that branch? Gotta be. That's what Kirchhoff's rule says. 8.5 volts. Knock, knock. I know two things. So it's going to be 8.5 divided by 40. This will be a little nicer decimal. 0.2125 amps. Oh! I got 0.2125 amps going this way. I got 0.14167 amps going that way. Don't they combine to give me I total? I think I total right here is going to be 0.21. So I'll even write it down here. I total is going to be 0.2125 plus 0.14167. You get 0.354? 3 out of 3. Now, if you got 0.354 amps, I would give you 3 out of 3. How would I do part marks? I go hunting for certain numbers. Martin, if I saw that number, I would give you 1 mark. If I saw that you had successfully moved the voltage to there, that would get you a half mark. If I saw that you had successfully found that current, that would get you a half mark. And then if I saw that you had added them together, that would get you your final mark, 3 out of 3. But if you got the right answer and you've written your work down somewhere, 3 out of 3. B. What's the voltage of the battery? Oh. I think what I'm going to have to do is either ski this run or ski this run, and if I add up all the resistors, that'll be the voltage. I better fill some stuff in. So this is going to be 0.354 amps, which is going to be 35.4 volts, I times R. And this is going to be 0.354 amps, which is going to be 8.854? Down here, because I can't do math in my head, apparently. Wow. 3.54 volts. But up here, it is 8.854 volts. Is that right? And now I can ski. It's going to be this number plus 8.5 plus 3.54. You get 20.9. So for work, how would I give out marks? If I saw that, that would get you 1. If I saw that, that would get you 1. If I saw either that or that, if I saw that you would use the 8.5, that would get you 1. And then if I saw that you had gone V total equals 3.54 plus 8.854 plus 8.5 to get 20.9 volts. That would be your final mark. Okay. You'll notice that one I didn't have to rewrite. Why? As soon as I saw they gave me 2 things, I figured I wouldn't need to. This one, I bet you I'm not going to need to rewrite. Why? They give me 2 things. I don't think I'm going to need to. They want me to find the power loss. Okay. First thing that I would do is I would find current here. And that's going to be V over R. It's going to be 6 divided by 4.5. And I get 1.333333. What else can I now? Oh, first thing I would do, Misha, actually is what? Yeah. I was bugging him earlier because he hadn't labeled a question downhill and it was making it tougher. What else do I know? Oh, 6 volts. Knock, knock. I know 2 things. 6 divided by 9 is 0.666666. You know what? So I'm going to say I equals 0.66 repeating amps. I think when these two combine, I think it's going to be 1.999999999. What's the total current really? 2 amps. 2 amps. Question's going to fall apart. In fact, I'm kind of done. You want the power loss? I'm going to go power equals I squared R, because that's on my sheet. I've got I, I've got R. I could find the voltage there too by going 10, but I'm going to go I squared R. It's going to be 2 squared times 5. It's going to be 20 watts. Yes? In terms of part marks, 1 mark if I saw that, 1 mark if I saw the 6 volts, 1 mark for that, and 1 mark for the answer. What's the part B? Oh! Suppose I remove the 4.5 ohm resistor, that guy, from the circuit. So suppose I remove this. What happens to the brightness of the 5 ohms? Okay, if I remove a resistor in parallel, what happens to R total if I remove a resistor in parallel? Increases. So, what happens to I total if I remove a resistor in parallel? If R total increases, I'm going to use I total equals V total over R total. What happens to I total? Decreases. And you'll notice the power loss that I calculated was using I total. R hasn't changed. But since power equals I squared R, power is less now. And so the bulb will be, correct answer, dimmer. If you got that, 1 mark. If somewhere you mentioned that R total increases and I total decreases, that's what I would need to see for 2 marks. Or you could just crunch it. If you physically crunch the numbers, anybody just crunch the numbers and find the new power? No one did. Oh, okay. I would give you full marks for that method, and you would find that the answer was less than 20. It's probably like 17 point something. Okay. Can you give yourself a lovely score, please, on your quiz out of 16, please? Terminal voltage. This is the voltage difference, the potential difference, that you actually measure between the ends of the battery or cell. If you stick a voltmeter between a battery, if you don't hook it up to anything, you'll measure what's printed on the side of the battery because no current is flowing yet. But every battery actually has an internal resistance. We can't make perfect batteries, which means when the current flows from positive to negative, so it would leave this way, it would go around, it would come back this way. When it flows through here, there is going to be a very tiny V equals I times little r drop. We use a lowercase r, Chantel, to signify we'd like that resistance to be small. In other words, if this is a 1.5 volt battery, we wouldn't like you to lose 1.4 volts going through here because that would only leave you 0.1 to run the circuit. So we want to make this resistance as small as possible, but it is there. Okay? So I is the current running through the cell, and that's going to be I total. Little r is the internal resistance built into the battery. Typically what we'll try and do is we'll tuck it either right behind the battery or right in front of the battery. And then often, not always, but often we'll do like a dotted line box around it. For example, if you look at your ultimate review, let me show you really quickly a question that has an internal resistance. I'm going to scroll. Oh, right there. That little r right there is built into the battery. Okay. E, this funky Greek letter sitting right there, this is an abbreviation for EMF, which stands for electromotive force. It's not a force. It's an archaic term that was poorly named, but it's the industry tradition. This is the maximum theoretical voltage. It's the one that's printed on the battery. We never get this. We always get less volts because you always lose a little bit going through the battery. V terminal, this is the actual voltage, and those little dots are designed to be the terminals. Okay. You know what? In my ski hill analogy, this little voltage drop right here, it's like when you get off the chairlift, you actually ski down a little tiny hill, a little bump before you go to your ski run. You lose a tiny bit of height just getting off the chairlift. You lose a tiny bit of voltage just going through the battery. Where the analogy breaks down, unfortunately, is because this is I times R, as current changes, the height of that hill changes. And in real life, the chairlift ramp getting off the chairlift doesn't change, but my ski hill analogy has carried us pretty good so far, so we'll continue it. Okay? So right there, this is the I times R lost in the battery itself. This would be the curly E, the EMF. This would be the terminal voltage, what you're actually getting left over for the rest of the circuit. As an equation, which I deliberately didn't put on your formula sheet, I guess the EMF equals the terminal voltage plus that bump, or the terminal voltage equals the EMF minus that bump. Okay. Example 1. What happens to the cell voltage as measured by the voltmeter if we close the switch? What happens to the cell voltage? And look how we're measuring it. This is the terminal voltage because it includes the bump. Let's remind ourselves that there is a little internal resistance. You can draw it in right there, little r, as we close the switch. Well, open, closed. With this open, the little bit of voltage that we lose going through the battery, the little bit of voltage lost is going to be I total times little r. Although with this closed, let's put a little I total right there. With it closed, the voltage loss is also going to be I total times little r. So you know what's going to make the difference here, Darwin? Really, what happens to I total when we close the switch. So you ready? When we add a resistor in parallel, what happens to R total? R total decreases. What happens to I total? And so strangely, when you close this switch, so maybe when if this is a 1.5 volt battery, when the switch is open, you might be measuring 1.4 volts across this. When you close the switch, will you measure a higher voltage, the same, or a lower voltage, not the same, because current has changed? You just said that this number gets bigger, which means this loss gets bigger. When you close the switch, now you might only measure 1.35 volts or 1.3 volts. You're losing more voltage traveling through the battery. So when you close the switch, the new voltage decreases. By the way, my proof, Martin, really you should start reading here and go this way. So I total increases because R total decreases, and therefore the voltage loss, which is I total times R, is going to get bigger. Otherwise, I just treat this like an ordinary resistor. But what I recognize is the EMF is what's printed on the battery. It doesn't include that internal resistance. The terminal voltage is that minus that. I also recognize if they don't give me an internal resistor, I also recognize if they give me a question like this right here, I assume that that voltage contains the internal resistance loss already, and they're just giving me the terminal voltage. Bada bing. Let's crunch some numbers. It says here, find an expression. Come back to that. Let's do example 3 with some numbers. So turn the page. Little note here, the EMF, the maximum theoretical voltage, is 20 volts. Also, I should say it is constant. The printing on the side of the battery doesn't magically change when you put it into a different circuit. So this is a battery that's rated for 20 volts. This is the EMF. Now the symbol for EMF is that curly E. Gonna make it, Hannah? Okay. It wants me to find the terminal voltage. Well, the terminal voltage is going to be the EMF minus what you lose going through the battery. Do I know the EMF? 20. Do I know little r? What? Do I know I total? Not yet. Okay. Label downhill. Now, you'll sometimes see instead of the dotted lines, they'll just put two big terminals on either end of the battery, and they'll show you that this resistor is inside the terminals, inside the battery. Do I know any currents anywhere? No. Will skiing help? Nope. You know what? I'm going to have to rewrite this. Wait a minute, though. These two resistors are in... What's our total? 2 plus 30, 32 ohms. Ha! I total is V total over R total. Be careful, this T stands for total. I never abbreviate terminal voltage with just a T because that's total voltage. I write the word term. This is not going to be the total voltage. This is going to be the net voltage that we're actually getting. It's going to be 20 divided by 32. How many amps are flowing through this circuit? 0.625? So if I want the terminal voltage, what we're actually measuring, if we put a voltmeter right here, what the voltmeter would actually measure, it's going to be 20 minus 0.625 times 2. Which is what? Hello? Oh, I typed that wrong. You missed a plus sign. You can't get negative. 18.75. That's how many volts are left over for this circuit. In fact, the other way I could have found the terminal voltage is I could have gone 30 ohms times 0.625. On your calculator, can you go I times R? Can you go 0.625 times 30 ohms? You'll also say, oh yeah, of course that has to be 18.75 volts because I started with 20, I lost a tiny amount, I have 18.75 volts left over for the circuit. That's the terminal voltage. The battery says 20, but what am I really getting out, Brian? What if instead of a 30 ohm resistor, what if I replaced it with a different resistor? This number would change, this number would change, this value would change. And that's where my ski hill analogy breaks down, because somehow that little bump at the top of the ski hill has a changing height, which doesn't happen in real life, but we've done pretty good, so we're okay. So I guess if you want me to find an expression, if I go back to example 2, the terminal voltage is what's printed on the battery minus what you lose going through the battery, I guess. But I'm almost reluctant to give you, they used to give this as a formula. I'd rather just have you ski and have it be intuitive, rather than having yet another unnecessary equation. Okay? By the way, the old equation, don't write this down, used to do that, plus or minus. The plus is when you're recharging a battery. You might say to yourself, Brian, why don't we just design batteries with no internal resistance? Actually, we need an internal resistance if we want to recharge the battery, and I'll show you that next. First of all, example 4, it says, find the terminal voltage and then find the internal resistance, labeled downhill. Chantal, did they give me total current? This question's going to fall apart. First thing I would do is put the total current down there, 1.5 amps, and then I would say, knock, knock. How many volts down here? Can y'all go to your calculators and do the math a little quicker without the long pause? Because I want to get through this lesson with time to spare. How many volts down there? 45? So this resistor uses up 45 volts. What's printed on the battery? What are we theoretically getting from this? What did we actually get from this? What must we have lost there? Oh, and how many amps are going through mystery resistor little r? So the terminal voltage, I can already tell you, 45 volts, because that's what was left over for the outside of the battery. If there had been more than one resistor, I just would have added up all of the voltages. And now I can tell you what little r is, because if V equals I times R, R equals V over I, how many volts do we lose going through internal resistor R? 5. How many amps are going through internal resistor R? 1.5. How big is the internal resistance of this battery? Okay. Now, if we made this resistor bigger, it would use up more voltage, and you wouldn't have voltage left over here. You'd have less voltage, maybe only 40, maybe only 30. And this is where we're getting our useful energy per coulomb, our voltage. So we want this to be small, but we don't want it to be non-existent. Here's why. What if we're charging a cell? Example 5. Let's come back to it, because example 6 is the same as example 5, but with numbers. Let's look at example 6. We're charging a 9-volt battery. That's one of those square ones with the terminals on the top. When you put your tongue on it, you get a little tingle. Those rectangular ones, you know the ones I'm talking about? Sean, how high? How many volts? How high? How many volts? You know what? Downhill is this way, this way, this way, this way, this way. It wants me to find the terminal voltage. I'll get to that at the very end. First, what's R total? Yep, 11. What's V total? Careful, it's not 30, it's not 9. What's the net voltage here in this circuit? 21. Because we gain 30 and lose 9 going backwards through the chairlift. What's the total current then flowing through this circuit? Well, that's going to be V total over R total, it's going to be 21 over 11. So I have 1.91 amps there, I have 1.91 amps there, and I have 1.91 amps there. But you'll notice we're going backwards through the battery here. We're going, well, let's see if we can figure out how many volts must be between here. And let's see if we can figure it out just by looking at these ones. Up here, how many volts do I lose going through this 5 ohm resistor? 9.5454545454. Yes? How many volts do I lose going through this 5 ohm resistor? Also 9.545455. I wrote amps again. Volts. 9.545454 volts. Okay. How many volts am I starting with? So if I start with 30, and then I lose 9.5454, and then I also lose 9.54. That's those two. I guess whatever voltage is left must be what these ones add up to. Is that okay? What do I get? 10.9. What's the voltage of the battery? How many extra volts am I getting going through backwards recharging this battery? That extra 1.9 volts is coming from this internal resistor. If I didn't have that internal resistor there, so that when I force current backwards, I get a voltage bump instead of a voltage drop, I couldn't recharge this battery. So we don't want to build a battery with no internal resistance because we can't recharge it for rechargeables. But at the same time, I don't want to have a huge resistor here. That would recharge it faster, but I'd have no voltage left over to run a circuit. And so this explains why when you plug your phones in, it takes so stinking long to recharge them. We can either have a small resistor, run lots of devices, slow recharging, or I could put a big resistor here, quick recharging. You're not going to be able to run much, though, because you're using almost all your voltage just to travel through the battery. Well, that's no good. That's the trade-off. Anyways, it wants the terminal voltage. V term is 10.9 volts, and that extra 1.9 volts, Ibrahim, is what's doing the recharging, and that's why it takes so long. Now, how many of you have a quick charging system on your phone? A couple of you? I'm not sure how that works. It wouldn't surprise me if they actually have a completely separate circuit with a different internal resistor that is only activated when you're recharging the battery, but when you're pulling current out of the battery, it bypasses that resistor. And that resistor would be a larger one, so that you can recharge it faster. That's my guess, but I haven't dove into how the quick chargers work. But that's a thought. This is the trade-off between rechargeable batteries, because the reason we can recharge the battery in the first place is we have to have an internal resistor, so that when we go backwards, there's a voltage bump, but we want that resistor to be as small as possible so that we can run stuff. So if you want me to find an expression for when the cell is being charged, the terminal voltage is the EMF plus the bump, because you're going backwards through the circuit, and so instead of losing voltage from that resistor, you're gaining voltage. You're skiing up the hill with your ski poles somehow. And that's why on the old formula sheet, this used to be the equation for terminal voltage. The plus was if you were recharging, the minus was if you were draining. I don't like the concept of the equation. I would rather say to you, oh, for Pete's sake, ski and use what you already know. I don't think we need a new equation. We need to understand the concept. What's terminal voltage? The EMF minus what you lose going through the battery. So in summary, if we're supplying energy to the circuit, if we're not recharging, then the terminal voltage is the bump minus I times little r. Oh, and I guess that means if they ask you to find the EMF, if they give you the terminal voltage and they say, hey, what's printed on the side of the battery? I guess the EMF is the terminal voltage plus I times R.
Yes.
And again, remember that the EMF, that's the constant one. It doesn't change because when I plug this battery into a different circuit, the printing on the side of the battery doesn't suddenly change to match the circuit. 1.5 volts for this is my EMF, but my terminal voltage, that all depends what I hook it up to. If I hook this up to something different, I'll get a different terminal voltage. If I hook up something different, I'll get a different terminal voltage because I'll lose a different amount because I total changes. If we're being recharged, okay, I guess it's the EMF plus I times R. You know what? I would just solve the rest of the circuit and see how many volts are left over between the terminals. I really wouldn't add this to your blue sheet as a separate, ooh, formula handy schmandy. What's your homework? First of all, you can now do every question in the ultimate review. Okay. However, I want to give you some practice with this too. So you can try number 1. I would probably sketch that out. Number 2, I would sketch that out. 3 is good. 4 is good. Skip 5, skip 6. 7 is good. 8 is good. 9 is good. 10 is good. And 11. Skip 12. Okay. And that's circuitry, my angels.